from one form to another. The delta for change. So the total energy stays the same. So energy is conserved, so it conserves energy.
Does that say energy from one form to another, or form?
Yes, from one form to another. Does this mean I have to stop translating my handwriting? I will say, when I taught elementary school, I made sure I wrote very neatly. When I stopped teaching elementary school, I thought, oh, I don't have to write that neatly anymore. And suddenly people started complaining about not being able to read my handwriting. All right. What do you suppose non-conservative forces do?
Release energy or don't conserve energy?
Let's go with the second one. They don't conserve energy.
They burn it.
They transfer energy from one object to another. So conservative forces will change it from one form to another, and we'll get into the forms in a moment. And non-conservative will just transfer from one object to another. So the conservative one will keep it in the family.
West Virginia.
All right, so let's talk about the forms. There are three things that are true about all things in classical physics, and we're doing classical physics. All objects in classical physics have a position. They are somewhere. They have a velocity. Actually, speed better here. Speed. Its direction doesn't matter here. And they have a mass.
You said this is for all conservative forms?
No, this is all objects in classical physics have these three things. The speed might be 0, but it's still 0 is a number. The position of an object, for each of these, there's an energy that's associated with it. Position is associated with, one of these markers would be dark. Potential energy. Speed is associated with kinetic energy. And mass is associated with rest energy. So when an object is transferring from one form to another, it's going from one of these to one of the other ones. And you're in luck. Because you're thinking, this is great, but where's the math? Here's the math. There's formulas. Yay. Ah, there we go. There is a formula for kinetic energy. So first off, the symbol I use for kinetic energy is a capital K. Kinetic energy equals 1/2 mv squared. 1/2 times the mass times the speed squared. Please notice, these are not vectors, these are scalars here. And this is one of the big advantages of energy, is that we don't have to worry about vectors. The downside of energy is we lose information about direction. So the plus is that they're scalars, the minus is that they're scalars. Momentum has the other problem. Momentum's advantage is that they're vectors, and the disadvantage is that they're vectors. So momentum, we maintain the idea of the direction, we don't lose that, but the math's more complicated. All right. This formula right here, I expect you to know cold. I believe the video I have is the formula to no cold. 30 years from now, if I run across you in the street and we do that wait, you look familiar routine, and then we identify who you are, I should be able to say, what's the formula for kinetic energy? And you should be able to tell me. 1/2 mv squared is the answer. Please don't expand it out. Don't do 1/2 times mass times speed squared. 1/2 mv squared. Now I'm going to ask for all of you to participate in just a moment when I ask what's the formula for kinetic energy. But Ty, I think you had a question?
You just answered it.
Okay. All right, here we go. All of you, and I am serious. What's the formula for kinetic energy?
1/2 mv squared.
All right, slightly in rounds, I appreciate that. Let's see if we can do it in sync, in unison. It's gonna be awesome. What's the formula for kinetic energy?
1/2 mv squared.
Like a chorus of angels. Excellent. I will ask that question but more than that time, but so far so good. Potential energy, there are several formulas. So if I ask you what's the formula for potential energy, the correct response is which one? It turns out every conservative force has its own potential energy formula. So conservative force correspond to a potential energy formula. So if we're talking about weight, or gravitational force where the acceleration due to gravity is relatively constant, I just pour capital G with little g approximately constant. The formula is mgh plus some constant. I think Hewitt drops the plus constant. But that plus constant gives us some freedom. If we're talking about the generalized gravitational formula, so G is not approximately constant. So we're talking outer space problems or, asteroid descending towards Earth. The generalized formula. We'll hit this in chapter 9, I think. The formula, negative big G, mass 1, mass 2 over R, plus a constant. Now, what the big G and the M's and the R, well, the M's are masses. R is the distance between the two objects, and big G's, that's the gravitational constant. We will get to that later. I'm just giving you the formula for right now. Something to sort of file away, and then later on, when we get to the big G, you'll be immediately thinking, like the potential energy formula. Ideal elastic force. F. I use S for spring, an ideal spring, because I saved the subscript E for electric, which is also conservative force. And the formula, 1/2 little k delta x squared. And I do recognize all it did was just sort of throw up formulas for you. We'll get into, MGH we'll use quite a bit. The others we'll get to them as we need to. All right, questions up to here? Yes?
In the tiny letters next to the formula for weight. Yeah, what's next to G? The little G.
That's two squiggle lines to represent approximately.
Okay. Now what are the letters next to that?
That, I wrote const because I got too lazy to write out the word constant. Ooh. Other questions? All right, let's actually use some of this stuff. Put it back.
Will rest energy have any
Oh.
equations?
Thank you, yes. All of you know the equation already. But if I asked you, would you write down the formula for rest energy, most of you would draw a blank, I suspect, but you know it. I'll start you out. E equals rest energy, the formula. Mass C squared. Now there's a slight difference from what you just said. It's m sub 0. And m sub 0 is called the rest mass. When you use the triple beam balance to find the mass of an object, the triple beam balance and the mass and you are all going the same speed. You're all right there at your rest relative to each other. That's the rest mass. The rest mass is just the mass that's measured when the object is at rest relative to what is measuring it. I put this in here for completeness of the symbol I use for this, E sub R. Oh, and the symbol for potential energy, as you would expect, it's a capital U. I suspect it comes from the German, but I don't know for sure. Some people will still stick with capital P, capital E for potential energy, and capital K, capital E for kinetic energy, and I know what you mean. But I will use big K and big U for kinetic and potential energy. Rest energy, that might be the last we ever deal with it. I just wanted it there for completeness. If we get to atomic bombs, rest energy becomes important. All right, let's get it. Oh, other questions before we do one example, maybe take a break, and then pick up with renewed excitement.
So that little g and that big G in the formulas that are right on top of each other are different numbers, correct?
Absolutely.
Okay.
This is one of the reasons why I want people to stop just using the term gravity without modifiers, because there are 4 things up here that students tend to call gravity. That, and that, and they are all different. Well, those 2 are similar to each other. But this is acceleration due to gravity, about 9.8 meters per second squared around here. Big G is a gravitational constant, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So, and then weight and generalized force of gravity. Yes,
What is C again?
over here,
Yeah,
just some constant.
okay.
And you get to decide what that letter C is gonna be. All right, here we go. I have a box, because why not? And I have the ground. It starts out 30 meters above the ground. Oh, let's make this a 5 kilogram box. And it ends up so it starts 30 meters above the ground, and I want to know how fast is it going 10 meters above the ground. No air resistance. So how far is it falling? Okay. We could, in theory, use, let's start at rest, so the initial speed is 0 meters per second. So we could use the stuff that we did in chapter 3 and figure out how fast it's going at that point. But we can be more sophisticated now, use energy. So the first question is, what are all the forces acting on this box while it's falling? I heard weight, and then I heard,
Can you repeat the question?
what are all the forces acting on it while it's falling? Weight,
Normal force?
what's it touching?
The box and the ground.
So
Oh wait, no, take
we
it.
stopped the problem before it got that far.
Gravitational pull.
That would be the weight. Weight is,
Okay.
it's not a separate thing, it's already included. All right, so it's the weight. Is that a conservative force or a non-conservative force?
Conservative.
Yes, so energy is conserved. So whatever energy I start with, it's got to be the energy at the end. Conserved energy means my total energy does not change. It's like you got a pie in front of you, no matter what you do to it, that pie doesn't go anywhere. You might have crumbs that might be scattered elsewhere, but you eventually you can put together all the pieces. That's probably a bad example because it does eventually turn into different kinds of energy. So scratch the pie example. My total energy, whatever this thing is, stays the same. So I have two types here. This thing is not bursting into flames. I don't care about rest energy. But I have kinetic, thus potential, initially, and that's got to be equal to the sum final. Whatever I start with, I end with. Remember, conservative forces transferred from one form to another. In this case, it's going to transform it, it's going to change it from potential into kinetic. Get ready, I'm going to ask that question again. What's the formula for kinetic energy?
1/2 mv squared.
Not quite as beautiful as the last time, but don't worry, you'll get another chance. So I got 1/2 mv initial squared plus, what's the formula for potential energy? Unison would be cool, but it doesn't have to.
Which one?
Thank you. The one associated with weight.
MGH plus C.
mgh plus c, so that's initial, equals, well, the same things except final, so 1/2 mv final squared plus mgh final plus c. Those are f's. Can I get rid of anything?
Get rid of the C from both sides,
Okay.
because the same C exists on both.
Yeah, so cancel, the constant just goes away. All right, can I get rid of anything else? Actually, before we get rid of any other letters, are any of these equal to 0?
Your initial kinetic energy is equal to 0 because it starts out not moving. That V squared is equal to 0, so then that whole thing becomes 0.
Yep, that's 0 because it starts at rest. Anything else is going to be equal to 0. All right. Now, can we get rid of anything else before we start plugging numbers in? All right, let's plug numbers in.
That's H initial, right?
Pardon?
That's H initial.
Yes, that's H initial.
I was.
So I got a mass of 5 g, let's assume it takes place on Earth. And what's my initial height?
30 meters.
Oh, no, they're-
There seems to be a general consensus that it's 30. Equals 1/2 times 5 times V final squared, that's what we're trying to find is VF, plus 5 times 9.8 times, what's my final height?
10.
Okay. Well, if that's 30, that's definitely 10. And now let's just multiply stuff together.
What's after clock?
So I got 0 plus, I'm not gonna write the 0 down anymore because it doesn't change anything. 5 times 9.8 times 30. Someone be kind enough. So I got 1,470 equals, I got 1/2 times 5, which is
2.5.
2.5 V final squared plus, and the last thing, 490.
490.
Okay.
Already got it.
All right, so now we have a math problem. We're solving for VF, so we need to get to it. What do? What's the first thing we should do?
Subtract the 490.
All right, let's get all this peripheral stuff over, so we get minus 490, minus 490. And so on the right-hand side, I got 2.5 VF squared, and on the left-hand side, 980.
Yeah,
All right, now what?
divide by 2.5,
Okay, so let's get rid of that.
392.
Thank you. 392 is equal to VF squared. We're almost there.
Square root it.
Yep, got to undo the square, so we square root both sides. And so I got VF equals
19.8.
units.